Let's take a look at acid-base indicators. Here are the assessment statements. We're going to describe how acid-base indicators work, and then we're going to identify appropriate indicators for a certain titration. So there's 3 points about indicators. The first point is indicators are substances that change color reversibly according to the pH of the solution. Second is different indicators change color at different pH. And third, most indicators are weak acids. All the indicators we are going to look at next will be weak acids. Okay, so let's start with litmus. Litmus is a weak acid, okay, and it has two forms. It has the undissociated form on the left, which is red, and the dissociated form on the right, which is blue, okay. Now because it's a weak acid, we can write this equation here, okay. So it dissociates to give H plus and the conjugate base, which is Lit negative, okay. So what happens if we add OH negative, if we add base? Well, basically we get this equation here, okay. The H plus and the OH negative react together to form water, H2O. Okay, and because we're using up the H plus, okay, the equilibrium will shift to the right. Okay, so when it shifts to the right, what color do you see? Well, you see the blue color. So that's why when you put litmus in an alkaline solution, it's blue. Next, what happens when you put litmus in an acidic solution? So if you add an acid, H plus, well, you get this equation. You get the H plus the conjugate base to give you the HLIT. So what color is that? Well, here it is. It's red. So the equilibrium has shifted to the left. Okay, because we want to use up this extra H plus. Okay, so when it shifts to the left, we get the red color. Let's take a look at another example, which is phenolphthalein. Again, it's a weak acid and it dissociates to give you H plus and the conjugate base, which we're going to call pH negative, which is pink. So when we add base, what's going to happen? This reaction here is going to react with this H plus, okay? And because we're using up the H plus, the equilibrium is going to shift to the right, okay? And when it shifts to the right, we see the pink color, okay? And next, we'll have a look at the effect of adding acid, which is H plus. So if we add H plus, it's going to react with the conjugate base, okay, to give us the phenolphthalein molecule, which is HPHPH, okay. Now actually this is colorless, okay. So the equilibrium has shifted to the left to use up all that extra H plus we're adding. So it becomes colorless, okay. Next we'll have a look at some indicators and their color changes. So we have litmus, methyl orange and phenolphthalein, okay. So indicators change color when the pH is equal to their pKa, okay. So up here we have pKind or pKa values, okay, and you can see litmus is 6.5, methyl orange is 3.7 and phenolphthalein is 9.3. So you can see around pH 6.5, which is about there, isn't it? Okay, litmus is in the middle of its color change. Methyl orange 3.7, which is around there. Again, that's in the middle of its color change from orange to yellow. And around 9.3, which is around there. Again, phenolphthalein is in the middle of its color change, okay? So The point where the indicator is in the middle of its color change is called the end point. Okay, so we've got the end point here for litmus, methyl orange, and phenolphthalein. Okay, so let's take a closer look at what we mean by end point. So here we have the equation for the dissociation of indicator. Most indicators are weak acids, okay, so they dissociate into H+, and we'll call it the conjugate base. Okay, so this is the conjugate base of the weak acid. Now we can write an expression for this, an equilibrium expression, okay. You got the H+ and the conjugate base on the top, and you got the weak acid on the bottom. Now, at the end point, okay, when the indicator is in the middle of its color change, the amount of the conjugate base and the weak acid are equal. Okay, so we can cross those out, because if they're the same, the top and bottom, we can just cross them out. Okay, so at the end point, in the middle of the color change, the amount of conjugate base and weak acid are equal. Okay, so when we cross them out, we're left with this here. Okay, K ind or Ka equals the concentration of H+. And then, if we take the log of both sides, we are left with the pH is equal to the pKa or pK ind, and this is at the end point. Okay, so when the indicator is in the middle of its color change, the end point, the pH is equal to the pKa or the pKind. Okay. Okay, so the end point range. The end point range is plus or minus 1 pH unit either side of its pKa. So for example, let's take methyl orange, and by the way, these are from table 16 of the data booklet. Methyl orange has a pKa of 3.46. Okay, so that means it'll change color. The middle of its color change will be pH 3.46. Okay, now the range at which it changes is plus or minus 1 pH unit either side of its pKa. Okay, about. So you can see that the pH range is 3.2 to 4.4. Okay, another example here is phenolphthalein. The pKa is 9.50, and the range at which it starts to change color is 8.2 to 10.0. Okay, right. Next, let's look at choosing the right indicator for different titrations. Okay, so we have a strong acid and a strong base. Okay, now you can see we have phenolphthalein here and methyl orange here. Now you should choose an indicator that changes color at the equivalence point. Okay, so you can see here that phenolphthalein and methyl orange, well, neither of them change color at pH 7, do they? Okay, but phenolphthalein is pretty close, isn't it? It's about, what, 8.2? So if you were titrating a strong acid and a strong base, okay, you could use phenolphthalein as an indicator because the range is pretty close to the equivalence point, isn't it? Okay? Right. Next is strong acid and weak base. Well, obviously here, right, phenolphthalein is pretty far from the equivalence point. Okay, the equivalence point is around 5, pH 5. Okay, well, phenolphthalein is not a suitable indicator, is it? So we wouldn't use phenolphthalein with a strong acid and a weak base. So let's look at methyl orange. Well, you can see that the color change in methyl orange is pretty close to the equivalence point, which is pH around 5. Okay, so methyl orange would be a suitable indicator to use, and as soon as you saw the yellow color, okay, then you know you're at the equivalence point. Next is strong base and weak acid. Well, here we have methyl orange here, okay? And you can see the equivalence point is up here, so that's pretty far from the equivalence point. So methyl orange would not be a good indicator to use. And you can see that phenolphthalein, its color change is right in the middle, and the equivalence point is right in the middle of the end point. Okay, don't forget the end point is in the middle of the color change. So phenolphthalein is a good indicator to use for a strong acid and a weak base. And finally, we have weak acid and weak base. Now, neither of these indicators is close to the equivalence point, so we wouldn't use either indicator, and you don't generally do a titration with a weak acid and a weak base anyway, so we won't worry about that too much. So the summary: when doing a titration, you should choose an indicator that changes color as close to the equivalence point as possible. Okay, so in the data booklet you're given the list of indicators, and remember the end point is where the pH is equal to the pKa. Okay, so it depends on what you're titrating. For example, weak acid, strong base. It depends on which titration you're doing as to which indicator that you use. Okay, so if we look at an example here, we got a titration curve, and we have a weak acid, and we're titrating with a strong base. Okay, so the equivalence point is around here, which is pH 9.5. Okay, and if you were to choose a suitable indicator, we go back to this list. Which one would be a suitable indicator? Well, you can see you want to choose one where the pH at the equivalence point is equal to the pKa, and yes, this one here, phenolphthalein, would be a good indicator to use for this titration here. Okay.